So we just talked about the options that we have if the assumption of normality is violated. And so let's try out some of those options. So first off, we need some data. So let's look at all the observations of sepal length from the iris data. And we're going to call that example data. And these data are 150 observations of sepal lengths from 3 different species of iris. But here we don't really care about the difference in species. So let's take a look at the histogram of the data. All right, take a look at it. It looks pretty normal. If we expand the window a little bit, it starts to look maybe a little less normal. Maybe it is skewed a bit. Here, the median is to the left, and that means that our data is slightly right skewed. If we take a look at our QQ plot, you can see that the dots are sort of making a straight line, but it's not perfect, and it actually is slightly S-shaped. You see, especially here at the top and at the bottom, the points don't necessarily make an exact straight line. And if we overlay a line onto that, we can see that a lot clearer. If we try to put a line of best fit on these points, we miss a bunch of points, particularly on the low end and a few points on the high end. So here we would say it looks normal-ish, but it's not perfectly normal. So maybe we need to either transform it or use a non-parametric test. There's a few options that we have for doing data transformations. And what data transformations are simple equations that you use to change the look of your data. It doesn't change the actual data itself. It scales the data in such a way where it makes it look and act like it's from a normal distribution. There's quite a few transformations that you can use, and certain transformations work better depending on what the distribution of the data looks like. For example, we have the log transformation, simply log your data, your y value, plus 1. We add the 1 because if there's any y values that are below 0, you're going to get negative numbers. There's the square root transformation, which is simply the square root of your observations plus 0.5. There's the reciprocal transformation, which is 1 over your observations. All 3 of those are typically used for data that is right skewed. If you are dealing with proportion data, which is not from a normal distribution, it's actually from a binomial distribution, you can do what's called an arcsine square root transformation. And that simply is you take the arcsine of the square root of your proportions. If your data is left skewed, you can do a y squared transformation, or you can do a exponential transformation where you take y and raise it to the power of e. And you do that in R by using the exp function. So let's take a look at our histogram again of the iris data. And as I said, it looks a bit right skewed. So we can try to use one of the transformations, see if we can make it look a little bit more normal. So first, let's try the log transformation. So the log transformation is simply the log of all of your samples plus 1. So here it's the log of example.data plus 1. And we can run that. Now, what we want to do is we want to compare between our non-transformed data and our log transformed data. And so I want to run par mfrow to give us 4 cells in our plotting canvas. And then we're going to run our histograms and QQ norms and our QQ line for our log transformed data. So here you can see it. It's already starting to look a little more normal. and we run the QQ norm and histogram for our original data. And as you can see, the log transformed histogram looks a bit more normal, and so does the QQ plot. It's not perfect, but it's better. Now we can do the same thing to check the other two transformations that are appropriate for right-skewed data. We can do a square root transformation, which is the square root of our example data plus 0.5. And run all of those plots. And we can see, okay, that works pretty well too. That maybe doesn't look quite as normal as the log transformation, but it does make our data fit the normal assumption a bit better. So now let's try the third type, the reciprocal transformation, which is simply 1 divided by your data. And if we look at that, we can see that that actually looks a whole lot better, both from our histogram here and our QQ plot. So I would say if we're going to go with a transformation, we're going to go with the reciprocal. Now, it's a very important thing to remember when doing transformations. One, you can try multiple transformations until you get data that looks normal. We just did that. That's a good thing to do. But you cannot try multiple transformations to get a p value that's less than alpha. These transformations are not meant to help you reject your null hypothesis. It's simply to allow you to use a parametric test on data that isn't perfectly normal. The third is that the statistics and the estimates that you calculate are on a transform scale. They are on a log scale, or they're on the exponential scale, or they're in a reciprocal scale. This is important because the data that you report should actually be your untransformed data. So you calculate means, standard error, standard deviation, all these different things on your untransformed data, and you report those, but you use the statistics based on your transformation. The reason why you do this is because most people do not think in terms of scales like the log scale or the 1 over y scale or whatever. No one can visualize that very well. So it's better to report untransformed data, but then state that your statistics were run using a transformation, either the log transformation, the exponential transformation, the reciprocal transformation, whatever transformation you use.